All right, we're going to try to handle some of this instruction per goal. We're going to look in this solution chemistry particular piece here. If you can get the gist of this on the fly, you're going to be just in fine shape. So take a few notes, okay? When we look at learning goals 2, 3, and 4 here, these are the ones we're going to deal with, all right? Some things you have to kind of keep in mind here. This first question, it says here, what are solutions? Well, you guys know what solutions are. Solutions are just homogeneous mixtures. Remember the term homogeneous? Okay, that's all a solution is. A homogeneous mixture. I hope I spelled that right, okay? But it's just a homogeneous mixture, and you guys should remember that from the very first semester, okay? So, and we've also talked a little bit when we were talking about the gas laws there. It referred to something like, okay, what are the components of a solution that involves a solid and a liquid? Well, we have a solute, and then we have a solvent, all right? When we start talking about a solute and a solvent, that's all really very, very, very simple, okay? Okay, the solute dissolves in the solvent. So if we've got our little cup of water right here, okay, and this is a perfectly drawn cup as always, and we've got our solvent. Our water in this case would be our solvent, okay? All right, and then we'll take a little bit of sugar here, like this sugar cube. We're going to take this beautifully drawn cube here, and we're going to drop that into the water, okay, and that will be our solute, okay, which is equal to that sugar cube. All right, so that makes that question there pretty darn simple. Okay, so shouldn't have any issues with that, dude, right? So I'm going to kind of get rid of some of this, and we'll consider the next question as we look at this. It says, what are the 3 factors that affect the rate, okay, all right, or the change in time in which a solute dissolves in a solvent? All right. If you look on page 472, like it talks about on page 472, when you're talking about a solute in a solvent, and we're talking about a solid in a liquid, all right, one of those 3 factors is going to be stirring, which obviously makes a little bit of sense. Okay, so if you we have our little sugar container again, if we were to stir that sucker up, all right, that would bring more solute into contact with the solvent, okay, dissolving it quicker, okay. Right. The second thing is going to be with a solid in a liquid, an increase in temperature. Okay. Generally, when you have an increase in temperature of a solid in a liquid, as a general rule, as you increase the temperature, you will also increase the rate at which that do dissolve. So we have that direct relationship. All right. The third factor is going to be particle size. Okay. And if you notice, when we had that cube, that sugar cube, okay, if we were to put that inside of the container and dissolve that dude, all right, that's not going to dissolve as fast as individual particles that we had. These are all individual sugar particles here. If this and this were equivalent in terms of number of particles, these individual particles would dissolve much faster than the other. So that too is also pretty simple. All right. Now the next question says, where does pressure fit into the mix? All right. Does it deal with gases, solids, etc.? Well, when we start talking about the effect of pressure and solubility, it affects the solubility of a gas. All right, it does not affect the solubility of a solid in a liquid. It will affect the solubility of a gas in a liquid. So if you increase the pressure of a gas in a liquid, it will generally increase the solubility of that gas in the liquid. Think of a soda pop, right? So you pop the lid on a pop can, you psh, and you hear that pressure, okay? You have more gas dissolved in that particular liquid, right? It does not have a general effect on the solubility of a solid in a liquid, so kind of keep that in mind, okay? We look at question F here, where it talks about saturated, unsaturated, and supersaturated, okay? When a solution is saturated, it can hold no more solute. All right, it can hold no more solute. All right, when it's unsaturated, that solution can hold more solute that will dissolve. When it's supersaturated, this word supersaturated, which is pretty cool, it holds more solute than is normal under those conditions of temperature and pressure. Look up on YouTube or something. You can see a really cool video. Look up sodium acetate and supersaturated solution, and watch a video of how that will crystallize with a supersaturated solution. That's pretty darn neat, guys. That's pretty darn neat. Okay, now here we look to G right here, and it talks about what do I mean by something being miscible or immiscible, and we already talked about that when we talked about the gas law stuff. When something is miscible in another substance, that means it will dissolve in that substance. Okay. Well, let's drop on down here to where it says what properties of water would lend itself to allow it, let's see, would it lend itself to allow it to dissolve in many but not all substances. Well, we've talked about this hundreds and hundreds and hundreds and hundreds of times. That is because of the polarity of the water molecule. Water is highly polar. Okay, with it being highly polar, all right, that means we have this partial positive end and this partial negative end, and we're going to draw this here. We've drawn this thousands of times. Okay, we got this partial negative end, and we got the two partial positive ends. That's a positive, by the way, and that's a positive. And because of the structure of this water molecule, it will attract other substances. Okay. Not all substances, but a lot of substances. There's an old term. It's like dissolves like. Like dissolves like. Okay, and once again, my writing is atrocious, but you can listen and write at the same time. What that basically means is, as a general rule, a highly polar substance will dissolve in other highly polar substances, and many times it'll also dissolve ionic substances. Okay, nonpolar, though, will not dissolve as a general rule in a polar or ionic. Nonpolar will dissolve generally only in other nonpolar. Okay. Now, when we look at these two situations here, situation 1 and situation 2, okay, and I think I did that backwards here, okay, talking about the glasses of water, and then we do to the next page with situation 3. Try to answer those questions. They're pretty darn straightforward. You shouldn't have any kind of trouble with those things, okay? If you do, let me know, and I'll help you through those things, all right? So, talking about solubility of substances in another substance. What we have here is that we've got a table right here, and I've got several different guiding questions that'll help you kind of understand this if you don't a little bit. But as a general rule, when you look at this table, this is kind of what happens with a lot of solids, okay, in water in terms of being able to dissolve. As you see, when the temperature goes up here, all right, the solubility goes up. In other words, that solubility references the number of grams of that particular substance that will dissolve in that substance. So like we said already, as a general rule, with a solid and a liquid in terms of solubility, when you increase the temperature, okay, the solubility of that particular substance will increase. Once again, general rule. It's a generalization. Not always happens that way. Here is another graphical representation of the same thing that we talked about. On this chart, you can see how that line goes upward as we increase the temperature. We have that temperature over here, and then we have grams of sucrose dissolving in 100 grams of water. So kind of interesting how that does relate to the table back there that you saw a few seconds ago. Here is another kind of cool graph that you look at here, and you can see like the solubility differences with respect to the various substances. So, you know, as we talked about, when we refer to any generalizations, that's exactly what it is. It is a generalization. Because you can look at some substances, like this particular one down here, okay, the YB2 sulfate, the yttrium, I can't say that worth a darn, so we're not going to. But notice how you actually have a decrease in the solubility with that increase in temperature. And when you look at the sodium chloride right here, all right, the sodium chloride, that's pretty much a flat relationship. There essentially is no difference in terms of change in solubility. You look at these other 4 compounds that they've included here, and there's a marked change, especially with the potassium nitrate, in terms of increasing the solubility with an increase in temperature, which is kind of interesting and kind of fun to look at. So just another graphical representation how things are like in the real world. Good stuff. Remember the generalization, though. Now, when we talk about a generalization, once again, dealing with different types of substances, if you look at this particular chart right here, here we've got three gases at a certain pressure, okay, so they kept the pressures the same. And as you notice with the gases, all right, when it's a gas, you have a decrease, okay, in the solubility, okay, with the temperature increase, all right, with the temperature increase. That's a T, okay? So with those particular substances here, this is generally what happens. So you have a decrease in solubility with an increase in temperature. And when you look over here at the solid substances above here, these are all solids that will be dissolved in the water, all right? They generally, as you look there, generally, not always, generally, you have an increase in solubility, all right, with an increase in temperature, okay? So that essentially takes care of those goals. Now, we're not going to worry about Henry's law right here, okay, but that basically states this right here with Henry's law. Okay, you're going to have that inverse relationship here, which can make it kind of interesting. You can do some mathematical calculations, but like I said, we're not going to worry. That covers those goals. We're going to go through the other goals in a few minutes, so have fun.